Another interesting thing about waves is they can bounce off of something. You have a wave going down here, it can bounce back. Okay, so you got a wave going this way, bounce it off, going that way. And you see this all the time. This is the idea of an echo. Sound waves bounce off, water waves bounce off as well. For example, down near Galveston, you have a seawall, and you have waves that come in, big waves that come in during a hurricane, and they hit the seawall and they bounce back. Okay, and that's actually a problem because you have to design your seawall appropriately. Because if the wave bounces right back, then what happens is you can sometimes amplify and get even bigger waves, which start gouging out the ground below the seawall, and that can sometimes undermine the seawall and cause it to collapse. And so this becomes a major issue with seawall design, is how do you design the seawall so it does not actually send the wave back and amplify the wave, and actually undercut the seawall, which can then fail during a hurricane, which is actually a really bad time for it to fail. Not that there's really a good time. And so this is an interesting sort of issue you sometimes deal with. Same thing with aircraft engines or rocket exhaust. You have sound waves that come out, and you don't want them to bounce and amplify to the point that you damage things. And so the other thing here about reflective waves is they're going in opposite directions. So let's just imagine we have a wave going this way and a wave going that way, and they're passing through each other. And so we have, y1 is going to be equal to some amplitude sine kx minus omega t, and that's the one going to the right. Y2 equals a sine kx plus omega t. That's the wave going to the left. And so the total is going to be y1 plus y2. And so that would be amplitude sine kx minus omega t plus sine kx plus omega t. All right. And so now we just got to evaluate this thing right here. And you look at it and you say, wait, we got sine plus sine. And you remember way back a long time ago when you were taking trig that sine A plus sine B equals something. Okay, so this is a trig identity. Okay, remember trig identities. Back when you were taking trig, whoever was teaching you trigonometry said you ought to learn these trig identities because one of these days you're going to need to know one. Well, guess what? Today's that day. Okay, so you now know the day that you needed to know this. And so you can write them back and say, oh, you were right, I did need to know that. Okay, so this is going to be the sine, 2 times the sine of a plus b over 2 times the sine of a minus b over 2. Okay, and so that gives us the this relationship right here. And so we look up here sorry. Okay, it's sine a plus b over 2 times cosine a minus b over 2. Sorry about that. Okay, and so now we plug all this up here together. So we find that y equals 2a times the sine of kx minus omega t plus kx plus omega t over 2 times the cosine of kx minus omega t minus kx minus omega t over 2. Well, that minus omega t cancels that plus omega t. This kx cancels that, and so what we have is y equals 2a sine 2kx. So that's going to be sine 2kx over 2, which is sine kx. Okay, and then we have cosine of minus omega t. Well, cosine of minus omega t is the same as cosine omega t. So we get something like that. Now, what does that look like? Okay, so at t equals 0, it's just 2a times sine kx. Now, as t changes, Sine kx stays the same, 2a stays the same, but the cosine gradually starts dropping. So what would happen is you would get something that looks like a sine, and it would gradually get smaller, and then get smaller, and then go negative, and then more negative, and then go back the other way. And what would happen is you would have certain spots right here that do not oscillate. We call those spots that do not oscillate nodes. And you have some spots here that oscillate a lot. We call those antinodes. And it would look like the wave is just sitting there oscillating, not doing anything. And it doesn't look like it's moving, even though you got the waves going back and forth. It looks like it just sits there oscillating. So we call that a standing wave. Okay. Now, the standing wave will fit the way I had it if both ends were like this. So you could get a standing wave like that, or you could get a standing wave that was like that, okay, or you could get a standing wave that was like that, okay, as long as they fit in there just, okay. So we call if the endpoints are fixed, then we call that the fundamental mode, or sometimes the first harmonic. So one that has a node in the middle is the second harmonic. One that has two nodes in here is the third harmonic. Okay, the fourth harmonic now notice in this case for the second harmonic the length is equal to a wavelength. Up at the first harmonic, the length is half a wavelength. For the third harmonic, the length is 3/2 of a wavelength. And for the fourth harmonic, the length is 2 wavelengths. And so what happens is that if you pluck a string on a musical instrument, then it's going to actually be mostly in the first harmonic, but it's also going to have mixtures of these other harmonics in there. Likewise, trumpet or any kind of brass instrument, a wood instrument or whatever, they're going to have this. And you can actually determine the note here by doing different things. So for a string instrument, you can change the length of the string, and that would change which wavelengths would fit in there, which would change what note it is. Likewise, for a wind instrument or something, you can actually change it by you have the different holes or so forth. When you put your fingers over the different holes, that forces nodes and antinodes in certain places. Even for a stringed instrument, you can put your finger on a fret and hold it, and that forces a node in that spot, and that changes what frequency will fit. And so you end up getting different musical instruments by using these different concepts right here. And so this is the idea of standing waves. And normally what I would do is at this point we would actually have a demo in class of standing waves. I don't have that, but I have found demos online for that, so I'll make a link to that.